nice introduction. Actually, this is my second week at Bell Labs, so so far so good. Week 1, join the team. Week 2, come to HotMobile. What I want to do in the next, say, 17 minutes is not really focus too much on the workshop paper, but what I want to try to do is convince all of the mobile sensing folks out there to carefully consider a recently emerging form of machine learning that I don't see being used very often in our community. Specifically, I'm referring to, of course, deep learning. What I believe is that it's going to help us build A, robust models that are able to operate in the real world, and B, help us manage these sticky resource issues. So I wanted to start this talk, oh, it's a bit dark, but anyway, I wanted to start this talk with some of the nightmares. Some of the nightmares that we face when we build things like wearables or smartphone sensing. Two of these problems are accuracy. And what I mean by accuracy is the fact that the models we use today are very brittle. We build them in the lab, and they maybe, for example, use audio to understand when someone's stressed, and we might use accelerometer data to know when someone's exercising. But what happens is when we release these devices into the wild, and we expose them to a lot of different people and to a lot of different environments, they start to fail. And we see their classification rates drop alarmingly. And this is actually in sharp contrast to if we see other types of machine learning in more mature domains. And in recent years, people have found that deep learning is enabling them to make breakthroughs in terms of their accuracy. So if I just take one example, speech recognition, and if you look at the work from companies like Google and Microsoft, what they're finding is that they can lower, for example, in the case of Google, the error word rate in their recognition of speech by 30%. So they're really having these breakthroughs in the types of accuracy they're getting. And it's not isolated to things like speech recognition. We're finding it's also happening in object recognition, where we have different forms of deep learning, specifically convolutional neural networks, are basically now forming the state of the art in this type of applications of machine learning. So the question that I ask ourselves with respect to accuracy, if you see below there I highlighted user behavior and context modeling. The problem is that there are no studies out there today that can tell us exactly how we should use these deep learning techniques to overcome some of these modeling problems. If we look at the different types of learning tasks they're succeeding with, a lot of them are strongly correlated to the types of sensing tasks that we care about. For example, speech recognition has a lot of overlap with some of the emotion type of recognition that we do with audio. And at the same time, for them to be able to start to achieve the levels of accuracy that they're doing, they're actually solving some of the modeling challenges that we face. For example, being able to operate in noisy environments and sort of generalize to lots of different people. Now, if I return to these nightmares that we face, the second one is resources. And by resources, I'm referring to our struggles with energy and computation. After looking at these models, I believe that because of the structure of these models, they're actually going to afford us a lot of new, interesting opportunities to manage our energy and computational constraints. To sort of explain and step back on what I just said, I want to explain a little bit further on how these models actually operate. This is just a very simple model of a deep neural network. Let me see if I can turn this thing on. Well, anyway, to the left-hand side, you have the input layer. In this, I guess you'll call it blue. What happens is you'll get a chunk of raw data, for example, audio. You'll partition it into small chunks and start to assign them to the different nodes on the entry point of the network. On the far right, we see these red dots. These are referring to the actual classes we're trying to infer. And in between, we have this sort of network of nodes or neurons. Their job is to try to capture the representation of the data as it travels through the network towards becoming an inference. Now, let me advance the slide a little bit. Right. The key operation that's happening inside these networks is that there's an activation function associated to each of these nodes. The role of that function is to look at all the prior nodes at the immediately prior layer. It's going to use that information to calculate its own state. And in aggregate, what happens is something sort of magical in terms of the fact that if you have a deep network of nodes, what you can do is start to learn very robust representations of the data that capture the types of classes we're trying to detect. And this is what sort of deep learning is all about. It's the process of learning these representations. Now, I just described a very simple form. There's a whole family of techniques out there, but the basic actions I was just describing are present in all of them. Now let me just ground this back towards how it relates to resources. I'm going to talk about two concrete examples of how, if you contrast the ways that we do machine learning on mobiles today, how these contrast to how it would actually operate under a deep learning scenario. So I'm going to talk about the scenario of speech identification. The resource I'm going to be worried about is what happens to the computation as we increase the number of classes we're concerning ourselves with. So in practice what this means is what happens if I want to start recognizing a larger number of people in my set. Now at the top left-hand side, I have a GMM pipeline. So that's, if you read any sort of mobile sensing paper today that's dealing with audio, most often you're going to hear about the extraction of PLP or MFCC features that are then coupled with a GMM model. And what this means is, at inference time, if I want to, for example, recognize Mary, I'll have two models. I'll have one model representing everybody else, that could be, and Mary herself. When the audio comes in, I'll look at the conditional probability of fitting that model, and I'll come up with a decision. Now what happens is if I want to expand this model out to recognize different types of people, or different people, I will, I'll basically have this additive process where I'll build and train a new model. That part's not the problem. The problem is at inference time I have to check that model again. Now what happens in contrast to a DNN approach is that if you train a DNN to recognize two people, or if you train a DNN to recognize, for example, 3 or 4, the structure of the model often actually doesn't change. You might spend a lot more time training the model, but often you can have a model that's very structurally similar, which means at runtime the overhead is very similar, but you can recognize, to an approximation, a number of different people. Now the second type of resource challenge that we often face in mobile sensing is that we have this issue of computation. Often we want to offload to the cloud. Now the way that offloading can be different under a deep learning scenario is as follows. If we compare the GMM pipeline, what happens is if we want to do a partition between local execution and a remote cloud execution, because it's comprised of algorithms of extraction of features and inference of the models that are hard to break up, they're rather atomic, what it means is it's hard for us to partition the split of execution precisely as we want it. In this case here, I've drawn a line in between the first two people and the last two people. This will cause redundancy in the fact that I have to extract the features both on the mobile and the cloud. And what happens is if I have, for example, an amount of local computation available to me that doesn't quite precisely match up with the effect of the model, is that I can't quite use that computation exactly how I want it to. Now if I contrast that to the DNN approach, because they're comprised of relatively small bits of execution, we're actually much more able to sharply partition how we want the execution to actually occur. And the reason this becomes extremely important is as we start to think about how we can come up with energy efficient execution on mobiles, we want to actually start to partition these networks more finely between DSPs, GPUs, and the cloud that are not going to be possible by other types of modeling approaches. Okay. So that was all motivation. While DNN is an interesting place to explore, both in terms of accuracy and resources, I now want to briefly tell you about the experiments we ran. What we had was a development kit that allows us to program at a very low level, the Snapdragon 800. You'll find these things on a lot of the smartphones available today. You also find them on smartwatches. So for example, the Android LG watch has a slightly simpler variant, but with still many of the same components. And what we designed was a system that focuses on inference time. So this first part of the system here, we did our offline training of some neural networks using toolkits, and then we would insert them onto a runtime running on the phone. Now this runtime leveraged both the DSP, the CPU, and the cloud. It's relatively simple. We use a heuristic to decide when we're going to have to go from the DSP to the CPU, but the focus of this heuristic was to force the DSP to execute as much as we can because the DSP is a lot cheaper in terms of energy than the CPU. Now to allow us to do some experiments in terms of partitioning between the mobile and the cloud, this runtime also allows us to assign fixed partitions in the network. Now what I want to do is show you two results from this system. This first result is looking at the scenario, two audio-based scenarios. This graph is showing you one, speaker identification, two, emotion recognition, to show you the types of results that we can have using a DNN in comparison to other types of modeling that you might normally would find in a mobile sensing system. What we're doing is comparing our DNN approach to three other models. And what we've done is we've provided the DNN with much simpler features. So while in both learning scenarios, these three comparison models are provided with a complex set of features that basically the de facto standard approach of extracting PLP features to describe both how speakers are speaking and types of emotional state. In comparison, the DNN is using just very coarse summary features, things like mean, modes, upper quartile, lower quartile, these very coarse indicators. And then what we're seeing though in the graph is the DNN is able, with a much lower set of inputs, to either outperform in the case of speaker identification or comparatively perform in the case of emotion recognition. Now what is actually going on here is that we have a form of representation of the learning occurring inside the DNN, where we have hidden layers being able to compensate for the missing computation extraction of the features. What this means is that we avoid this heavy computation of extracting the features. The DNN is actually having this really interesting trade-off where the energy profile of executing the DNN is very similar to a very simple model of a decision tree. And in comparison to the GMM, it's much, much cheaper. But again, you'll see the DNN is providing, comparative performance in the emotion recognition and the best performance in terms of the speaker identification. Now, the final piece of evaluation I want to show you is that of the DNN with regarding to how it's using resources. You remember I mentioned how it should be able to scale much more efficiently in terms of how we increase the number of classes. So on the left-hand side here, we have a graph. It's comparing the DNN's scaling in terms of how long it takes to compute. You'll notice that it's in red, it's at the bottom, and it's being compared to the GMM, which is increasing in a linear fashion as we have to add in these other models to describe each person speaking. And you'll see that it's actually, it's very similar in performance to the decision tree. The other type of result I wanted to show you is how the DNN can very smoothly partition its workload. Now what we did here was we partitioning the network between the cloud and the local device. You can see here that it's a very smooth partition that's much lower, it's about 10% lower than what's possible with the GMM. The GMM also has this choppy feature. So if you zoom in, you see the resources that are being choppily consumed, and it's hard to smoothly go from different levels of resources being executed on the cloud and on the mobile device. Now, this is actually going to become critical, again, as I mentioned earlier, when you start to want to partition between things like the DSP, the GPU, and the cloud. So that's what I prepared for today. I actually wanted to also just summarize briefly what the focus of this talk was. And I want to do so in the following way. I want to talk about two research challenges that I think are very important for us moving forward. The first is understanding how we can model users in context using deep learning techniques. There's some very promising techniques in the way that deep learning is able to use unlabeled data, something that mobiles are plentifully able to generate, but we're actually unable to use effectively today because all our models are supervised. So deep learning has these facilities to us, we just don't know how well they're going to work. Similarly, as I've sort of just touched upon, sort of really just on terms of an initial exploration of how deep learning is able to overcome and learn better features that are different from the conventional hand-tuned features we've been using in the past. The second question I want us to explore is how we can scale down deep learning so that it can run on mobiles and phones. If you look in a variety of system conferences, there's been really interesting work in how you can scale deep learning upwards. Basically, these folks have been discovering interesting ways of allowing these algorithms to consume increasing amounts of data. And what they're finding is as you do so, these models work better and better. What I argue is that there is an equally important systems problem to be done, which is exactly understanding how we can also scale these models downwards so they can then be run locally on mobile devices. And finally, I want to point out that we've shown some initial results towards both of these problems today with the initial prototype. So with that, I will take questions.